Elon Musk once emphasized, the more affordable we can make the car, the better. For Tesla, affordability isn't just about swapping batteries or materials. It's about rethinking the entire manufacturing process from the ground up by breaking old production habits, eliminating unnecessary steps, and reorganizing operations according to the natural flow of materials, labor, and robots. Costs begin to decline in a steady, predictable manner rather than fluctuating unpredictably. The $10,000 price point for the Model 2 is not just a marketing slogan. It emerges naturally from this disciplined approach, driven by pragmatic and measurable production metrics. One of the subtler yet transformative changes in the Model 2 production line involves the treatment of exterior finishes. Traditional painting processes are notoriously expensive, consuming up to 50% of a factory's electricity and producing over 60% of CO2 emissions per car, while 10 to 15% of vehicles often require repainting due to dust or defects. Tesla sidesteps this by removing the conventional paint shop entirely, assembling the car body in a raw state, and applying color and surface finishes at the final stage through pre-finished panels. Though seemingly minor, this adjustment dramatically alters the cost structure. Eliminating the paint shop reduces energy consumption, removes a frequent source of defects, and cuts time spent on work-in-progress vehicles. Consequently, the time a car remains on the production line drops by 20 to 30%. On a line capable of producing 250,000 Model 2s annually, a 25% efficiency improvement translates into an additional 60,000 vehicles without increasing factory footprint. Energy savings are equally notable. Removing the paint shop reduces electricity use by 0.6 to 0.8 megawatt hours per car, cutting roughly $80 from each unit's energy cost. Installing the color skins is remarkably quick, taking just 10 to 12 minutes for the 6 major panels like the hood, rear bumper, doors, and side panels, with 2 to 3 robots handling positioning, fastening, and bonding, followed by technicians verifying gaps in finish. Compared with traditional painting, which requires 6 to 8 hours, this is a radical acceleration. The precision of robotic work ensures consistent quality across shifts, while the use of color-last panels benefits owners long after production. Minor scratches or impacts no longer require repainting. Panels can be replaced in under 90 minutes at a service center, whereas repainting similar areas could take 2 to 3 days and cost double. Standardized panel design and detachable installation cut repair costs by 40 to 60% and improve color durability, since the skins are produced in controlled supplier environments. Achieving consistent color and texture across batches is critical, as eliminating inline painting shift quality control to the supply stage. Tesla leverages spectrophotometers to maintain delta-E color deviations below 1, nearly imperceptible to the human eye. With surface quality assured before final assembly, alignment precision reaches under 0.5 millimeters at panel joints, rivaling premium vehicles. Overall, color-last panels achieve 3 key objectives simultaneously: reduced energy consumption, faster assembly, and lower maintenance costs, potentially saving up to 20% of total production cost per car and cutting VOC paint emissions by half. Customers benefit directly through reduced downtime, lower repair expenses, and higher resale values, demonstrating that this innovation is not a mere cost-cutting measure, but a practical application of Tesla's reverse production philosophy, eliminating one of the costliest automotive stages while maintaining high quality. This shift in approach extends to the drivetrain, another traditionally delicate and multi-step assembly process. Conventional methods separate motors, inverters, gearboxes, and cooling lines into multiple subassemblies to minimize errors, but Tesla integrates all of these components, along with modularized battery packs, into a single pre-assembled pallet installed as one unit. This replaces 3 to 5 separate assembly stations, with robots tightening bolts to precise torque and angle, while sensors verify placement before the car moves to testing. Installing the powertrain as a unified module increases production rhythm, aiming for 35 to 40 cars per hour per optimized station, resulting in roughly 280,000 vehicles annually with 2 shifts over 50 weeks. The modular battery pack follows the same philosophy, divided into 2 or 3 standardized modules with integrated cooling and high-voltage connectors. Technicians can replace a defective unit in 2 hours rather than the 2 to 3 days typical for Model 3 or Model Y packs. Modularization also enables rapid adaptation to supplier changes or upgrades by updating pallet profiles and robot programs, limiting line downtime to under 24 hours per change. Assembly as a single unit simplifies quality control through alignment sensors, 3D cameras for gap verification, and torque data tracking for each bolt, while quick connectors with pressure sensors detect leaks or distortions early. The result is fewer assembly errors, reduced rework, and a tighter, more refined final product. Additionally, the modular design supports remanufacturing after 3 to 5 years, allowing battery modules to be rebalanced and tested, motors inspected and bearings replaced, and certified components returned to inventory, reducing waste and long-term repair costs. The Model 2's final production stage further embodies Tesla's innovative thinking. Instead of a single long quality check, end-of-line testing is split into fast and slow tracks, rapid automated checks for electronics and software, and slower, more detailed inspections for aspects affecting real-world feel, such as leak testing and vibration. Electronics testing is completed in 8 to 10 minutes, faster than many European benchmarks, and software defect rates are kept below 0.5% through immediate over-the-air fixes, avoiding bottlenecks typical in other factories. Slower checks, including rain chamber and vibration tests, are optimized with data-driven real-world profiles, reducing testing times while ensuring under 1% failure rates and fixing minor defects within 15 minutes. Tesla also eliminates prolonged storage by shipping vehicles directly to nearby delivery hubs, cutting inventory by 50 to 70% and reducing micro defects from environmental exposure by 20 to 30%. This final adjustment, combined with modular drivetrains and colorless panels, reduces the total cost of ownership and ensures affordability is tangible rather than theoretical. In short, Tesla's approach to the Model 2, cleaner production flows, rapid electronic checks, stringent real-world validation, modular components, and optimized logistics, transforms the manufacturing process at its core. By minimizing time spent in the factory and maximizing operational efficiency, Tesla reduces costs that directly affect the buyer, making a $10,000 EV a realistic outcome rather than an unattainable dream. Affordability for Model 2 is a result of meticulous process design, faster assembly, smarter end-of-line testing, and modular, repair-friendly components, creating a vehicle that is not only cheaper produced but also cheaper and easier to own for years to come, demonstrating that true cost reduction comes from thoughtful production architecture rather than cheap shortcuts or incremental tweaks.